safety in reinforcement learning. So just, I think everybody, now this is kind of background material. So we have a stochastic control system. So x at time t plus 1 is a sample from a probability distribution p, which depends on x at time t and u at time t. And so we know that the stochastic control problem is to design this policy pi as a mapping from xt to the input space to minimize some additive, for example, additive expected value of additive cost subject to these dynamics. And so the dynamic programming give us the optimality conditions for this policy, which we can then use to synthesize the optimal control. So this is just sort of a high-level introduction. And over the past 7 decades, the community has made a lot of progress to dynamic programming, to addressing more general objectives such as safety reachability, which we'll talk about, risk, multi-agent formulations, and also approximate dynamic programming approaches to address computational tractability. But there's still some challenges such as tractability, computational tractability, and incorporating real-time data. So here in the picture, this was some of the work I did when I was a PhD student a while back, and we were using dynamic programming to do aircraft trajectory planning. And here we had this weather forecast data, and this shows regions that have storm are likely to have a storm because it's the precipitation level. And we model this with the stochastic sets, and then we try to design aircraft trajectory that's fuel optimal and also with high probability avoids these storm regions. But as soon as we put a few aircraft in this picture, then the tractability becomes a problem, scalability, and also it's hard to incorporate real-time data about forecasts and so on. At the same time, we know that reinforcement learning has been very successful, and this approach in the model-free case, we basically throw away the dynamical model, or we assume we don't know the model, and we try to learn the policy by directly interacting with the system. So our system becomes like a black box, and we apply some policy, we observe the trajectory of the system, and we can measure our cost and then refine this policy. And it has been this class of reinforcement learning algorithms have been very successful in solving some challenging problems, but ensuring safety is still an open and challenging problem. And so here I want to talk a little bit about some of the safety aspects. And I also want to say it's an active area of research. So many people in the control and reinforcement learning community work on incorporating safety in data-driven and learning-based controllers. So this is just a little bit of an overview of some of the different methods, just to highlight that's active topic, and I'll try to bring in some of our insights into the problem. So first, I actually want to talk about reinforcement learning and stability, and because this is a school about work at the intersection of control and reinforcement learning, I thought it would be good to talk a little bit about some of the control concepts we are interested in and how they connect with the RL approaches. So let's look at how do we incorporate cost in reinforcement learning. So usually we have 3 different main approaches. So we have a finite horizon cost, and as we will see, with this cost, we can also encode probability of trajectory being inside a safe set. We have an infinite horizon cost, but here we either have to do a discounting or averaging so that we get a finite, so this series would converge. And so if we have a discounting, what we're going to first talk about is it will be not possible to encode safety or stability concepts, just as a kind of a overview of what we can or we cannot do. And with average cost, we could incorporate these properties, but learning, I think it's a little bit harder and requires more assumptions. So what I want to first highlight is this discounted sum and why it cannot incorporate, for example, stability concepts. Okay, so maybe you have seen definition of stability in the beginning of this lecture, in the beginning of the week. If not, let's just briefly also just talk about the stability. So when we have a dynamical system, what's the notion of a what do we mean by stability? So first, we can talk about stability of an equilibrium. So this is our dynamical system. Let's say we don't have any noise. Discrete time xt plus 1 is a function of xt. And we can also generalize all of this to continuous time, but it's easier to talk about discrete time now here. And the equilibrium of the system is where this f of xt is 0. I want, I'm looking at continuous time, discrete time. F of xt, basically it's a fixed point of this, so the dynamics don't change. So, okay, so if we look at the inverted pendulum system, so here is, if this is the inverted pendulum, we have an equilibrium at the upright position and we have an equilibrium in the down position. And this, so stability, let's also briefly talk about it. We say the equilibrium is stable in the sense of Lyapunov. If we start close, we start close to this, close to this equilibrium, the initial condition is close, then we can ensure that the trajectory also remains close to the equilibrium. Okay, and we can also refine this and talk about, for example, asymptotic stability. The trajectory also converges to the equilibrium. So this says that if there is some small deviation, we should stay within this some small neighborhood, and this says that we should converge to it. Okay. So intuitively, this equilibrium is unstable because a small perturbation the pendulum would fall, and this equilibrium looks stable, right? Okay. So now we just want to see why, like just as an example, why the infinite horizon discounted cost couldn't ensure in general stability. And the reason I bring this concept is because I see that in reinforcement, many people are using reinforcement learning and they're trying to apply these methods to dynamical systems and infer something or think that we can stabilize a pendulum, but we have to be careful how we design our costs. And let's do a simple example. Here we have a linear dynamical system. And this is, I think you saw linear quadratic control in the first lecture. So this is the quadratic cost, and it's an infinite horizon problem. So we can put a discount factor. So it's a well-posed problem, and the LQ, our problem is to find the sequence of inputs that minimizes this cost. So xt here is in Rn, it's continuous space, ut in Rm, then wt is a zero mean noise with sigma squared variance, and these are positive semi-definite, positive definite matrices, so this is a well-defined problem, and gamma is a discount factor. And so you have seen, I think, linear systems, this is kind of the starting point when we look at control, because many systems, we can approximate them by linear models, and we have a very rich theory for controlling linear systems. And also this LQR can give us intuition about studying other continuous state and action space dynamical systems. Okay. And you also know that the optimal controller is linear feedback. So the optimal cost is given by x0 transpose px0 plus this term that depends on the noise. This is trace of p, and p is a solution to this algebraic, the so-called Riccati equation. Okay. And the optimal controller is linear. Just kind of a brief overview. But the point is, we know how to solve this problem, and we can characterize the optimal solution. Okay. And now let's just look at a very simple example. Let's take, this is just one example, there are many of such. A equals 2, B equals 1, so we have a scalar system. R and Q are 1. And you can see that for if the discount factor is in this range, the controller will not be stabilizing. What does it mean? So let's say that you have gamma equals 1/4, then A plus BK. So this is a closed loop. So the dynamics in the closed loop are written as xk plus 1, A plus BK, xk. And this is greater than 1. So this diverges. Okay. So we have an unstable system. And it's not hard to come up with this example. You can imagine that the discount factor lets you forget about long-term behavior of the system, right? And there's also a lot of work that try to look at what conditions we would need so that if we optimize some discounted cost, as we often do in RL, we might have a stability for the system, okay? And another thing I want to highlight is that this is a problem of the cost formulation. It has nothing to do with what RL approach we use, because I looked at there's a lot of blog posts now when you look at RL, anything about RL, and they try to stabilize an inverted pendulum with, I don't know, a discounted cost or a finite rising cost. And then there were some observations that the Q-learning approach seems unstable and so on. And after a while, the policy started to do this and that. But we just know theoretically, we don't have any guarantees if we use discount cost, if we want to, for the stability of our closed loop system. So this is like one of the first things I want to highlight when we use RL. First, we have to understand what problem we have, what can we do with it, with this type of cost, and what can we expect. We cannot expect to use this method if stability is an important problem, if it's an inverted pendulum, or inverted pendulum is just a classical example, but it's used as a model for, I don't know, rockets flying and bipedal walking and so on. Did you have a question? Yeah, so if you can increase the gamma, so also this paper, Romain, derives some conditions. Actually, just increasing gamma generally is not enough. So, for example, obviously, there's some additional properties you need. You want your system to be controllable, and which means, maybe controllability, it just means that you should be able to steer the trajectory of the system from an initial point to a final point, okay? And you want the cost that you're designing to be with your dynamics to be detectable, meaning that you should be able to observe if your cost only sees some subset of the state space, because you're only penalizing some subset, then your system might be unstable and you don't observe that from the cost, okay? So you also need this detectability. So for sure you would need these properties, and then with sufficiently large discount factor, there are cases where you can prove that you will have a stability of the closed loop system. But the catch is that you would need your dynamics to know, actually, to check these conditions and to design that discount factor generally, okay? And in RL, we wanted to solve the problem without knowing dynamics and in a model-free fashion, or if we know it, we just throw away that knowledge. So then it's not consistent, like this kind of looking at this. Yeah. Stability. Okay, I can explain it for linear systems because it's easiest, but this is a concept that also holds for nonlinear system. Let's say you have xt. Okay, first let me just say it in words. So detectability, it's related to the concept of observability, and it says that if you see the output, well, in this case, let's say in the LQR problem, you can write this cost X transpose QT as X transpose C X. This is the cost on the state, right? And then you can call this the output of the system that you're measuring, okay? And observability says that you should be able to, by observing this Y trajectory, reconstruct your state. Intuitively, that's what it says. Now, if you happen to have a linear system, and it's not related to, you don't need the control for that. It's just a property of the output you're measuring and your dynamics. Then it turns out that observability is equivalent to some rank condition between A and C. So you can write and detectability as well. So it's you form the observability matrix, and then you need some rank condition or some eigenvalues to satisfy a certain property. We can go more in depth, or I can give references, okay? Does it help? But intuitively, it just says that the cost, whatever you're penalizing here, this is what you're measuring. That whatever you're measuring should capture all the information, like about the state of the system, or sufficient information about the state of the system. Okay, yeah. Yeah, that's a easy. Yes, exactly. That's also one way to say it. Yeah, that's also intuitive. Yeah, yeah, exactly. That's also intuitive. And when, at least in LQR proof of the Bertziko's book, he uses that argument to argue that if your cost is converging, that you have also stability of this closed loop system. Okay, good. Other questions? Okay. So yeah. So when we use RL, and I think often, but I do a little about, we do some experiments, but maybe a little bit more theory. But I see that often people use discounted or finite horizon cost because for some things that I will also mention, but maybe just we should be careful that we cannot reason about infinite horizon properties of our dynamical system generally. Okay. So also what about safety or reachability? So let me briefly introduce that. These are also fundamental control concepts. So safety, so let's say you have a subset of the state space, okay, and you want to ensure that your trajectory always stays in that set, okay? So that's called safety, or also known as invariance, okay? And if you have a stochastic system, then you want to maximize the probability of your state trajectory being in that set. Reachability is about the state trajectory reaching a goal set, G, okay? You want your state trajectory to be somewhere, okay? And these are dual concepts in the sense that if you define S as complement of G, then you can probability of S would be 1 minus probability of G. So by studying one of them, you can study the other one. So can RL cost capture safety or reachability? Maybe based on what we saw, it shouldn't be too hard to imagine that generally not, but it's not maybe super obvious either. Because at least when we talk about infinite horizon, it turns, again, a discounted cost or finite horizon cost cannot ensure that, because it forgets about this long term, okay? And there is actually a result, this is from 2022, that says that given a reachability specification, for any discounted reward, no matter how you design your discounted reward, there exists some transition kernel such that the optimal policy corresponding to this reward will not be the optimal policy for your reachability. Okay. So discounted cost cannot capture safety or reachability. Okay, and that's the idea of this proof is also they basically create a case like this is a four states dynamical system, and so you have a reachability objective. This you want to reach S1, and if you basically follow, there are two policies, like taking A1 or A2 deterministically, and with probability 1, if you take this, you would eventually reach S1, but it might take a very long time, whereas you can, with some probability, P1, you can go this path and reach the state, okay? And you can, for any discount factor, you can adjust these P's, okay, so that the optimal policy for the discounted case, because it's more greedy with respect to near term, would be to take this shorter path, which means that not with probability 1 reaching that, whereas the optimal policy for the reachability specification would be to take a path that with probability 1 make sure you reach that, okay? But there are also more examples that go back also to this older paper, which is on arXiv, and additional discussions. So maybe for the first, oops, a lot of my files open. Okay, for the first part of this talk, what I wanna convey is that if we care about infinite horizon property, performance of our system, discounted or finite horizon cost in RL would not help us generally. So as we said, we cannot argue generally about the stability of inverted pendulum, for example, if we are using the discounted infinite horizon cost, no matter what training algorithm we are using. Would an average cost help? Indeed, in this paper, they also show that if you have a safety specification, you can always you can define an average reward criteria so that the optimal policies corresponding to that also are optimal with respect to your safety. So average reward is better, and you can imagine because it doesn't have this forgetting about the future. But I think reinforcement learning with average cost is more challenging, and I would be interested also to discuss with those who work on that. And one of the challenges is that in maybe intuitively, I think in reinforcement learning, we try to infer something by seeing finite samples of the system, and we may need to see for average cost, we may need to see very long sequence. Basically, with finite sample, we may not have enough information. A formal way of saying this is also called a simulation lemma that tells us when can we, if we learn. Suppose we have an MDP, and we have an MDP that's epsilon close to it, and if we learn a policy for this, actually, I think I have to look up. I don't have it exactly precisely the formulation in my head to be able to tell you. But there is somehow about approximation properties. If you're seeing an MDP that's close to the original MDP, and you optimize that one, that policy might not be close to the policy of the original MDP with the average reward. Okay. So it's harder to do reinforcement learning with average reward, but I think it's important, and I think it would be an interesting direction to also focus on, that I'm interested at least. And but now for the rest of the talk, I talk about some of the things we did so far, which is on focusing on safety specifications, but in finite horizon, because they're should be easier to handle. Yeah. Oh, yeah, that's a very good question. So there are many ways, I think, to define also safety, especially nowadays with RL. There's surveys on RL safety. I'm using the term safety and control means that basically your trajectory stays inside a safe set. Okay, so let's say if you have collision avoidance is your goal, you want to make sure that your states don't get into a collision set. So now I'm just using this definition. Yeah. Other questions? Yeah. The discount rate that keeps a certain dynamics state? There are some research on it, like this was one of the papers I cited, but as I mentioned, it usually requires knowing the dynamics, and so a priori we wouldn't know, but if we know the dynamics, we could, for example, in this case, I think in that example that I give you, the discount factor had to be, usually it has to be sufficiently large, but that sufficient is not a priori known, and certainly would depend on your dynamics and costs. Does that help? Okay. Other questions? Yeah. Okay. In the sense that, so if we take S to be complement of the G, the goal set, this is our entire state space, and this is a complement, and then probability of being in X take away G is equal to 1 minus probability of being in G. So if you solve for one of these properties, you can infer about the other property. So if you have an algorithm that can maximize probability of safety, then you can also use it for reachability. You take X take away G, X set minus G as your safe set. Does that help? Okay. Other questions? Yeah. Yeah, so usually we assume we know, for example, we don't want to get into collision, and we say that the distance between the cars should be above some threshold. Usually we know it, yeah. Our dynamics, in RL, we assume we don't know, but the specifications, usually we assume we know it, yeah. Other questions? Okay. So now I want to talk about finite horizon safety. And finite horizon, these are some of the applications. I said we do some applications that we work on in the lab. So we're using reinforcement learning for robots to learn how to assemble and construct the structures. This is a collaboration with architects. And we're also using reinforcement learning for and inverse reinforcement learning for autonomous driving. So this is from our lab and the simulators we developed, and this is from the Carla autonomous car simulator environment where we implement our algorithm. But a lot of these problems that we look on are finite horizon, so it's not a stability or an infinite horizon invariance property. And we also have safety constraints, collision avoidance, or robots not getting into each other or to humans. So that's sort of a motivation for us. And I also, again, as we already talked about safety, how we define it, but I just have it now here again. In the finite horizon, we say that the trajectory satisfies safety given S if xt remains in S during this time horizon, and it satisfies reachability if there exists T in this time horizon that the state trajectory reaches G. And it also, we say, reach avoid problem, which is contains both of those as subproblems, is that given an S and a G, we want to, the specification is that there exists some time in this finite horizon that xt goes to G. And for all prior times, xt is also in the, x tau is in the safe set, okay? So always you're safe, and then at some point you reach the goal set. And we're gonna, because this is the most general one, I'm gonna focus on this one, but they're all related. Yeah. Well, I said let's focus on finite horizon, because in infinite horizon with combination with RL, it becomes hard. Yeah. I mean, you can also have specifications, over all of them over infinite horizon. Yeah. Okay, and so we looked at also we looked at Safety Gym is an OpenAI suite for testing safety of different RL algorithms. And we tried to see how do they incorporate these safety constraints. And there they also, by safety, they mean collision avoidance, and by reachability, they also want to reach some goal sets. And so what we find is that usually, this is based on looking at different papers, it seems that in our L community, safety and reachability are either captured by the reward or by a constraint. So either you put for safety, you put a high negative reward for violation of constraint, for not being in the safe set. But in general, it's very hard to tune this weight. How high should this reward, this negative reward be that it will ensure your system is safe? So if you also, you want to put it as high as possible if safety is important, but if you make it too high, also there are problems with numerical problems with your approaches. And also the other approach that we found very commonly is this constraint MDP approach. So you formulate some constraint, but again, either through some discount factor, you try to incorporate that, and it's usually some summation, some discounted constraint. And these don't have any a priori guarantee on safety. And we also developed such class of algorithms in the reinforcement learning, and this is a test suite from this safety gym of OpenAI. So let me explain it to you. There is some robot whose dynamics we don't know, we don't see it. As far as we're concerned, is black box. And this is from the camera views, that's what the robot sees. It has to find its way to the goal, and it has to avoid these objects. If it basically the safety constraints are this, and these objects could be moving, and it doesn't know their motions, and so you can train you basically based on getting these camera, it's an end-to-end learning example. So you parameterize policies with neural networks and you try to directly learn what should the robot do by interacting with the environment. And we developed also some algorithm towards this using this constrained MDP approach, and we compared it with other approaches, and ours was an interior point approach, and here we're comparing with the Lagrangian approach, and what you see is the reward that the agent is collecting and the safety. But what I want to highlight is very hard to interpret what does this mean, in the sense that in the CMD, here we are basically having an discounted some cost, and it doesn't directly relate to the safety. So it doesn't tell me if it's a really safety critical system. It doesn't, if I look at these numbers, it doesn't really tell me how, if I hit the obstacle or not. Okay, so it's not a direct measure of safety. And that's when I think a lot of times when in RL people talk about CMDPs and safety, it's hard to interpret the results we get about actually safety of the system. Okay. So we try to look at how can we cast finite horizon safety and reachability into this finite horizon CMDP, and I want to talk a little bit about that for the rest of the talk, so that it's so that we have formal a priori guarantees that if we solve this problem, we have this safety. Which what we want is we want that probability of xt, for example, inside some safe set be greater than some threshold. Okay, so something that we can interpret, nothing that no discounted additive costs that we cannot directly relate. Okay, but yeah. Well, you can play around with these environments. Sometimes you can choose it to be a like a four-legged robot, or it can be a car, or it can be a bipedal walker. Basically, these environments are configured in a way that you can choose, but you assume that you don't know that dynamics. Does it make sense? You don't know anything, so it just try to it's kind of, it's coming from a control background. To me, it's like, why would you solve the problem like this with this end-to-end learning? Basically, you just look at camera images, and by making enough experiences, you try to find your way so you don't know a priori. By looking at these are like, your camera is your sensor, and you don't know your dynamics. You don't know how these might move and where they are, but your sensors give you information. And you want to learn by direct interactions. Does it make sense? I have questions. Yeah, because you don't know a priori where these objects are. So in some sense, you're learning what to avoid. Yeah. Yeah. Yes. Yeah, that you can also do. If you do it in a receding horizon way, and then you define appropriate your terminal cost to go, and your invariant set that you want to put your state in, that you can also do, but it would become receding horizon control. I guess it wouldn't become RL. Yeah. But when you do that in receding horizon, basically the controller you apply, you resolve the problem at time t+1 based on the new data you get, and then you apply that, and then you resolve. And I think in RL we don't do that, because we learn the policy and then we implement that policy unless we resolve. Does that make sense? Okay. We don't resolve at every time that we take a step, whereas in receding horizon, the stability concerns with this receding horizon approach that now we replanned, and we, yeah. Okay. Yeah, good question. I can talk more offline. Yeah. Yeah, they can be changing. Yeah, exactly. Yes. Yeah, so you can probably look it up, and they have a paper that goes with it as well. The environment, these boxes could be moving around. Also, in our paper, we have wait, stopped moving. Okay, now. We also give details about the environment, but here, for example, I didn't go through the details of this because I didn't want to make the talk about comparison of our approach with other approaches. What I want to come back to is, again, how do we incorporate safety in a way that we can have a prior guarantee. So here in this black line, first we trained on one environment, and when we try to I guess I think we changed the dynamics and the obstacle. No, it was always a car environment, and then here we go. I wrote it, change the task. We made the goals smaller, so you can change the task. Supposedly, if you make the goals smaller, it would be harder to learn. And we wanted to show that, okay, we are still having better safety compared to that at that time state-of-the-art approaches, but still it's hard to interpret exactly what we are doing with these numbers in terms of safety. Okay, other question. Okay, so I'm going to present the work now about this. The work that I want to talk about now is with my PhD student, Ting Ting. The work here, which builds upon the work with my former student, Ilnura Osmanova, PhD student, and who started to look at this, she started to look at it in this CMDP framework. And then later on we said, okay, but that's not quite, doesn't quite incorporate safety. So we tried to look at how can we incorporate safety in this framework. Okay. So here we go. I focus on the reach avoid because it incorporates, so we want to reach a goal set and avoid unsafe sets. So it incorporates safety and reachability. And let's say that this is our specification. It just, we're looking at the set of trajectories such that at some point in time in the finite horizon, they reach a goal set, and at all prior times, they are in the safe set. So we can just, if we have some other cost function, we can formulate, we want to find a pi star such that it minimizes this running cost subject to, now this is our constraint. It's very interpretable. If I look at these constraints, I know what I want from our system. If the safe set is a collision-free set, if I achieve this, I can tell that, okay, my algorithm has safety with this probability, okay? Now, so it directly encodes the specification, but how do we formulate it in a way that we can solve it with some machinery that we already know? And this reach avoid problem also has been looked at by many people in the past, but not in a learning approach and not in a CMDP learning approach. CMDP approach very recently was another colleagues looked at that, but not again in the learning approach. But I will give you a little bit of a background about that. So now we want to understand, get intuition about what happens when we have such safety and reachability constraints for our dynamical system. And the first thing I want to show is that our policy may no longer be Markov, it might be history dependent. Okay, so let's talk about, let's say that history at time t is the x0, u0. So the sequence of states and inputs that we have observed at that time, and we can have a policy that's history dependent. And you can have a policy that's Markov, which means that it just depends on the current state. And if you're in an infinite horizon setting, we also care about whether our policy is stationary. And so in a CMDP, when this is just like a running cost, additive cost, at each stage, it's adding the cost of that x and u. This is a classical constraint Markov decision process formulation. And we know that the optimal policy here is Markovian. So here is the kind of what you see in the RL. Now here it's a constraint that looks exactly the same type as the cost. This is called the CMDP framework, okay? Okay, so what we want to see is that if you have a safety reachability specification, it may no longer be the case. And the main intuition is that we don't have an additive cost on each the trajectory at each time, our cost, which is coupling the entire trajectory because it's on the probability of xt at each time being in the safe set, for example. So here we can create an example. So here is our dynamical system. This is the initial condition, and these are the states. And it let's say over a horizon of 3 AB. Okay, sorry. Oh yeah, it is correct. Sorry, this is just a safe set. So the safe set is the ones that are in green. So we want our trajectory. We want to make sure that the trajectory with high probability stays in the safe set, and we have also a cost for reaching this state E. So these are unsafe, the greens are safe, and there is a cost in one of them, okay? And then we can look at the probability of safety, so it's probability of having ABDE, and then the expected cost. So it's here, probability of X3 equals E, because it's a 1 here, and it's probability of going ABDE or ACDE. And then the safety of a Markovian. So, okay, so the control only comes here. So here, there's no control here. With probability P, it transitions here, and with probability 1 minus P, it goes here. And the only time we are controlling is here by choosing this with which probability to go here versus go down. So in a Markovian policy, so this U0 would depend just on the D. And in non-Markovian policy, it would depend on the trajectory that the state took to get to D. It could depend on a history-dependent policy. And so safety would be P pi of U0 conditioned on D. And this is the cost, which P pi of U0 D plus 1 minus P pi of U0 D. So it's just pi of, so this is our probability of choosing U0 conditioned on D. And in a non-Markovian policy, the safety is the same, and the cost, now it doesn't add up to pi of U0, because here it depends on which trajectory we took. And so if you look at then this problem of minimizing, because our cost is this, pi of, in a Markovian case, pi of U0D, subject to this will be our optimal cost, because we would put a probability of 1 minus delta divided by P here, so that we satisfy the constraints and minimize the cost. And if we have a non-Markovian policy, because we know which trajectory we took, we can just put a 1 minus delta over P on this one and put a 0 on this one and have a cost that's 1 minus delta. So the optimal non-Markovian policy has a lower cost than the optimal Markovian policy. So, okay, well, the summary of it is that when we have a safety or reachability constraint, because it's a constraint like that is coupling the state trajectory, you may have a policy that's not optimal policy that may necessarily not be Markovian. So that's one difference than the classical, let's say, a CM constraint Markov decision process that's been studied. So we may need history-dependent policy. But we will see that it's actually not so bad, and there's a way to convert it to a standard CMDP. So I just make a pause to see if there are questions. Yeah. Oh, I guess, sorry, I try to, usually in the CMDP literature, you maximize some reward subject to some rewards being above a threshold. I try to put it in the control. I mean, you can, I guess if you have some delta, you can take it, oops, there you go. You can take it to this other side. You can basically formulate your objective so that this becomes less than or equal to some threshold. Okay, some threshold. 0 is not important. Yeah. Okay. Okay. Okay, I realized this reference, like the reason I had this reference was we're generally looking at also continuous state and action spaces under which conditions the optimal policy is Markovian in this class of problems, and there are some works that looked at that. Okay, But we saw that if we have now a safety or a reachability or a reach avoid constraint, something that's coupling the state trajectory, the optimal policy might be history dependent. But what we're gonna, now what we're gonna see is that we can introduce additional states, and we can, with these additional states, we can again cast a standard CMDP, okay? So let me explain that, and this is a trick that's used in people who work on formal methods. So you are given a specification and you wanna formulate, you want to make that specification into a cost function, for example, or into a standard problem. So how do we do this? In this particular reach avoid case, I explain it to you. Let's say we introduce some 3 states, 0, 1, and 2, and our new state space becomes the original one, product space with this Q. Okay, and these states basically encode if we have reached, if we went out of the safe set, if we are in the safe set but not goal set, or if we have reached G, okay? And so the transition probability for the original states is just as before, but for the QT, so these are the states in this finite state machine, they're decided by XT and QT. So we start here, we are in the safe set, not in the goal set. As long as we are in the safe set, not in the goal set, we Q stays in as 1, and as soon as we go to safe set complement, we go to the state Q equals to 0, and we stay there forever. And as soon as we go to the goal set, we go to state 2, and we stay there, okay? So this, with this, now we have a MDP over this extended state space, and what we can see is that, well, clearly, if we have this trajectory of original system, we can generate this trajectory of this finite state. So it's completely determined. But also we see that X, the trajectory is satisfying this reach avoid specification if and only if Q at time t equals 2. The cost can remain the same. So the cost, then we can define a final cost over this extended state space. I think I have it here. The final cost over the extended state space to be 1, the indicator function of QT reaching 2, okay? And now, this is for the constraint. The cost is the original cost of our MDP. Okay, and with this formulation, now we have a CMDP that's exactly, so this was our original specification, and this is our new CMDP. So it has a cost on the final state of this extended transition dynamic. So it has decoupled this this cost that required us to reason about the probability of the entire state trajectory. I just pause to see if there are any questions about this. Yeah. Exactly. Yeah. And the main issue was that originally this is a property, I mean, with this example, for example, that is on the entire trajectory, and we want to just make it like an additive cost or a cost just on the final state so that it's in the, we can use it with the tools that we already know. Because once we have this construct in this extended state space, and this is now a CMDP, and we know that looking for Markovian policies, but over this extended state would be sufficient, and that's good news because it would be hard to search for history-dependent policies. And we can also, if we get the optimal Markovian policy, here we have finite horizon, so time varying, then we can also map it to a history-dependent policy, because we just, by looking at just the XT of our system, we can figure out what QT is, and then figure out what policy we should apply. I didn't separate, I extended the state space. So I extended it to be this product of some finite state which captures if I had reached my goal or not, or if I have been unsafe or not, and the original state. I extended the state space, and because now my goal becomes a reachability, I have to reach this one, okay? So I have to, at the final horizon, if I am here, it means that I've always been safe and I reached the goal set. Does that make sense? Yeah. Other questions? Yeah. Yeah, it's a good question. I mean, this is a very, very small problem, reach, avoid. But if you have more complex specifications, no, it actually it can become very large. Q can become very large. So that's something, I mean, I don't talk about it here, but it turns out there are classes of this temporal logic formula. So reach, avoid, or safety is a subset of that you can cast as an automaton, and then you can formulate some reachability. You can formulate your specification as a reachability on this product space, but this automaton might be too big. Yeah. Go ahead. Yes. It's not action masking or state masking, because if I understand what action masking is you basically, if your input is large, you would saturate it. If I understand the terminology from the RL, I think when they're called masking, you would use saturation, because if your input if you have too much high of a force to your robot, maybe you just like saturate, like don't apply all the magnitude. Is that correct? Is that what action? This is what my superficial understanding of action masking. Yeah, but here a priori we are incorporating it in the specification so that the policy we learn will never violate. So we don't have to a posteriori mask or saturate. Does that make sense? Yeah. Other questions? Yeah. Oh, sorry. This should be X take away S. So it's complement of S. To be consistent with my notation, it should be the state space unsafe set. It's unsafe set. Yeah.
So basically, in this framework, we are allowed during learning to violate.
No, we don't want to violate the constraints. Oh yeah, I will go to that. So first, so far we just want to make sure we define a problem that if we solve it, we can say that our state trajectory stays in the safe set, for example, with high probability. So far, we want to see how to formulate that in a framework, and then we want to see how to learn it. And when we want to learn it, we're going to look at how do we learn it safely, in the sense that during learning, we don't violate as much as possible, because everything is a stochastic and there's always a probability of, but I will formalize it. Yeah. So for now, it's just on how do we encode safety and reachability specifications into this CMDP framework, because now we found a way, if we extend the state, to have this extended state space, then we can formulate a final terminal cost on, basically this cost just depends on QT, because if we reach this QT in that transition system, it means that we were safe and we reached the goal set. And so we can look for Markovian policies here. Okay, good. Yeah.
So the the cost functions constraints in terms of the induced chain by the policy.
Induced mark. No, I haven't tried that. I know. Yeah, I haven't. Why are you interested? Just just curious. Okay. Yes. Okay. Yeah. Could be interesting. We can talk also offline. I don't think I have thought about that. Okay. Good. From this part, the takeaway message is that we can formulate safety and reachability constraints on trajectory as a constrained MDP over an extended state space. And so safety by design, we know what we are asking our system to do because it's not some additive, it's not some high penalty that we don't know how to tune, or additive cost that may not be directly related, or a discounted cost. And also, as I answered to one of the questions, any specification that can be captured by an automaton, we can cast it as a reachability problem on an extended state space. And so we can formulate these more complex specifications if they come from some formal language, also as a CMDP. Yeah. The framework just says that we want to find a policy such that you ensure probability of any trajectory that results from your policy being safe is above a threshold. Yeah. Mm-hmm. So it would be any trajectory, like the probability of the trajectories are, above a threshold. Good. Okay. So now we get to a little bit of the learning aspects. So we form it as a CMDP because now we can look at Markovian policies in CMDPs, and also we want to know how do we use learning to solve this problem. So also a bit of the history of the problem. Safety and reachability are very old problems in control. So people looked at it in deterministic setting, then a stochastic setting. For example, does there exist a Markov policy that maximizes safety, probability, and so on? How do we formulate it? And then very recently, they also looked at it as how can we formulate as a constraint if we have other objectives, not just safety and reachability. And this is also the work exactly that we did. And the next thing that we looked at is how do we also solve it with a learning approach. So that's what I want to talk about. So here is the problem we want to solve. But whatever I say, actually, it doesn't. From now on, it doesn't matter exactly what this is, except that it's a CMDP in the classical sense. So it can be an additive cost, but it's not a cost that couples the trajectory. Now here I wrote everything in terms of this RXT and QT, but it could be, you could try to also imagine looking at this in a Markov chain over just some state space, and you have some constraints that is either additive or is just on the terminal cost and so on. And the learning problem is we don't know the dynamics, but we have trajectories of the system. We can query the dynamics by applying a policy and getting the trajectory. And we want to also make sure that the policies during learning are safe. So if we formalize it a little bit more, so we don't know our dynamics, and how do we do it? And I'm going to talk about our approach, which is based on policy gradient approach. So we want to parameterize these policies, okay, with some finite dimensional parameter. Again, we have time varying policies because I have a finite horizon objective and constraint, and so I have a parameter for every time. And so because I parameterize the policy, then I can write the objective function as j of this parameter, and the constraint as some constraint on this parameter. And the data, we do not know our dynamical system, but we can apply a policy and we observe the trajectory, and we want to design an algorithm such that pi of theta k satisfies the constraints and converges to the optimal policy. That's our goal. Okay, so we call it safe learning, because we want to also make sure that if we are interacting with the real system during the interaction, we make sure that we don't satisfy the constraints. So let's see what kind of problem. Let's go a little bit into more detail. I think you saw policy, for example, gradients in the course earlier. So this is, we can have different parameterizations when we when we do a policy parameterization, so we can have a linear policy. So in this case, this would be some theta transpose X plus some noise. We can have a Gaussian parameterization where this is a Gaussian distribution, and the mean could be some neural network parameterized by theta, and then there is a variance which could also be parameterized, or we can have the softmax class of policies and so on. What all that does is that it reformulates our CMDP problem as a constrained optimization problem. That's why we like to do finite parameterization, because here we are searching in the infinite dimensional function space, and now by parameterizing the policy, we're searching over a finite dimensional space, and it's actually a classical constrained optimization problem. But there are a couple of challenges, because we don't know the dynamics. We don't know the J and C analytically. We don't know what those expectations are there with respect to this transition kernel, and both for the objective and the constraints, okay? So, and furthermore, this J and C, so they're not only unknown, they're also generally non-convex. So we are asking to design some algorithm that goes to the optimal point of this objective function, let's say here, without knowing what the safe set is. So it's like a black box, and we want to make sure also during learning we satisfy the constraints. So it's that this is the challenge. But once you parameterize policy and you look at this problem from an optimization problem point of view, it just becomes a constrained optimization. Okay. Is there any question? Yeah. Yeah, so basically now what we did, we said that our constraint, which was this, all of this means that, for example, we had a reach avoid, but we can think of safety. We want to make sure this was exactly encoding probability of XT being in S greater than some threshold, okay? That's what this C is. Yeah. But because our policy is parameterized, now it's just some constraint on parameter theta. We just don't know what it is, because that's very hard to, like, we don't know P, and we cannot anyhow, even if we knew it, it would be hard to analytically get the J and C. Okay, other questions? All right. I give you a high level idea of the approach that we look at for this. And so we're looking at policy gradient class of algorithms, and we look at anterior point approach. So the idea is that we design a barrier function, okay, high level, that we want to that ensures we stay in the feasible set, and we estimate the gradients of J and C from the sample trajectories, and then we take if we know the gradients, and if our functions have some Lipschitz continuity or smoothness property, we know how small we should take our step sizes, so that if we are currently safe, in the next time step we are also safe, because we know how fast, if we know the Lipschitz or smoothness constants, we can know how fast the function is changing. Okay. So let's go through these steps. So we look at a log barrier for the constraints. So the log barrier grows to infinity as you approach the boundary of the constraints. So it creates some barrier to stay there. And by making this log barrier, our constrained optimization problem becomes converted to an unconstrained optimization problem. And as eta is coefficient goes to 0, the solution of this log barrier function, which is an approximate solution of the original constraint problem, converges to a true solution. This just comes from optimization, log barrier interior point approaches in the optimization literature, okay? So this is not from us, but the idea to use it for this problem is what we did. Okay. Now, because we made an unconstrained optimization problem, at least we removed one challenge to some extent. So we can look at gradient descent, just like policy gradient. We can update the parameters of the policy as we don't have any constraints. So we just theta k plus 1 is theta k minus some step size times the gradient of the log barrier. And so the questions you want to ask. Would this approach converge to the optimal policy parameter? How do we create? We don't know J and C, so we don't know the log barrier and its gradients. How do we create estimates of this? And how do we choose the step size? And I'll just briefly talk about this in the next slides. Are there any questions? It's a barrier, so it's a barrier on this constraint. It's an approach to the to solve this constraint optimization problem. So we're not directly limiting the actions.
If we design the barrier for that, and it should safety, but it will stop exploring the other ways.
Yeah, it becomes harder for convergence. It slows down the convergence, yeah. But you don't want to maybe think about actions because now we don't have anything. We just have parameters. We just have parameters of our policy. So everything we talk about now is in terms of the parameters of the policy. Directly, we're not talking about the actions. But if we satisfy these constraints, it means that the policy, so pi of theta k, would ensure okay, maybe it's C of theta k greater, less than or equal to 0 would imply that pi of theta k ensures that probability of xt in the safe set over this horizon is greater than 1 minus delta, okay? Does that help? Yeah. So this is just because we formulated the constraint in a way that it's capturing this property. Okay, so this is our constraint, this is an equivalent. I'm writing the problem in terms of the parameters. So this is an equivalent problem in the parameter space. So if this is satisfied, the policy from it would satisfy the constraints we set. Does it help? Yeah. Yeah, now we must assume we start with a safe policy. So we need to assume that we start with a policy that satisfies this condition so that we can make sure that recursively as we try to optimize it, we also satisfy it. So our assumption would be that because our goal is we want to make sure that iteratively these policies learned from the policies parameterized by theta k satisfy the constraints. We have to assume that at least at the very first instant we are satisfying the constraints. Okay. Okay, so this is like making a barrier. It grows to this function, then would grow very large as you approach the boundary, and we're going to take the step size as small enough so that we don't get there. This constraint or this one? Yes. Yes. Yeah. No. Okay. If theta k, if C of theta k will be, if your algorithm ensures that this is satisfied, so if you have an interior point approach, an interior point optimization approach would ensure that the iterates would always stay in the feasible set. And then by the definition, this will be satisfied. Okay. But okay, but we will see that we cannot, with only with some probability we satisfy this. So there's another double probability coming on top of that. So maybe that's what you're referring to. Yeah, but maybe I think that it would be, so now we just have to think about in the parameter space. Okay, now we're trying to solve an constraint optimization problem. All we are doing is that we want to solve a constraint optimization problem, but our objective and constraints are unknown, and we want to have a feasible iterate method. So now the problem is just in the optimization space. It happens that if we have a feasible iterate method, this constraint will be satisfied. But what we show is that we have a high probability feasible iterate method. Does that make sense? Yeah. Yeah, it's a good question. So it depends on the application, but we should have some. So for example, if we have no idea what a safe policy would be, then it seems it may not be a good assumption, but usually the idea is that maybe you have an idea of what would be safe, but that's a conservative policy and you're trying to optimize it. But in any work that would look at safe learning, that would be just like the first assumption, because if your first point is not safe, then first you have to find a way back to safety and then continue with this algorithm. Yeah. Good. Other questions? Okay, so now we're just basically looking at optimization, black box constraint optimization, and we want to have feasible iterate method. But we will see that it again, our L comes again, because when we want to estimate these gradients and know how to take the step size, then we have to again use the properties of our dynamical system and policy parameterization. Okay, and that's the first place. So the first observation is that because of this RL problem structure, and if we do correct parameterization of policy, we will have this so-called approximate, in this case, approximate gradient dominance, which means that as the log barrier gradient, let's for now ignore this eta, when the log barrier gradient gets very small, then theta is getting close to theta star, optimal parameter. So this is this means that the first order stationary points of log barrier are approximately optimal policy parameters. Okay, so the function may be non-convex, and but still it has some property that if this is the optimal, we can bound the suboptimality of j of theta by looking at the gradient of the log barrier. Okay, and we will look a little bit into why this holds under which policy parameterizations, and in particular the so-called Fisher non-degenerate policies. So this is just okay, the definition of it, that what should this policy satisfy. So we need to use a parameterization such that the policy satisfies the following conditions. So the expectation of, so let's say you have pi of theta and you take the expectation with respect to the probability distribution that's induced by that pi of theta for your states and actions. And then if you look at this quantity, this matrix, it has to be lower bounded by some mu f identity. Okay. It's a technical assumption, and it turns out that there are policy parameterizations that satisfy this, such as Gaussian and Cauchy, and some policy parameterizations don't satisfy it, but the intuition of it is that if you have the policies that are more exploring and are more random, this mu f will be higher. So if you have a Gaussian parameterization and you have a variance that's not vanishing, that variance, basically, this mu f is characterized by that variance. So if you have policy parameterization is a smooth, you have a smooth class of policy, and you have this Fisher non-degeneracy property, then you have this approximate gradient dominance, which is used in which has been used a lot in the past decade in reasoning about convergence of gradient descent in non-convex optimization problems, and then also in reinforcement policy gradient in reinforcement learning. So this, these are just the eta was the term in our log barrier. This epsilon bias is again another approximation that goes to basically epsilon bias is small for if your parameterization is rich in the sense that it can approximate large class of functions. If it can if for example you have a parameterization that includes all functions, that epsilon bias will be 0. And then for some other classes, if for example you have a neural softmax, so it's parameterized by a neural network, and as the depth of the network gets high, this epsilon bias goes small. And then here's where that Fisher non-degeneracy comes into play, and here was from our log barrier. But all this is saying is that you can bound the suboptimality of some point theta by the gradient of the log barrier. So if you design an algorithm that for which log barrier gradient becomes a small, where it's very small, then you know that you're almost optimal. You have an almost optimal policy. Okay. So it motivates gradient descent. But it just a bound. I mean, yeah, it depends on the C and eta and all of those, but you may not know them. It just says that there is a bound on suboptimality of some theta, which is eta is a design parameter. Epsilon bias depends on your policy parameterization. T is the horizon, and this, we don't need to know it, but it just says it's bounded by this much. And so if you make eta small, and then you make epsilon bias small, this will be small. And then if your policy is it's exploring very well, then this will be large. And so this whole thing will be small. If you mean? But I haven't talked about constraints at all. So this is just a property of this log barrier. Okay. Yeah. So if we basically this eta, yeah, it's as it goes to 0, you approach the solution of the constraint optimization problem. Yeah.
Is that how to say that there's the gradient dominance?
No. Yes. I mean, this is about gradient dominance. So that's the term that in a standard gradient dominance you would see, but we have some extra terms here. Yeah, exactly.
Is this gradient dominance an assumption?
No, we show it. But for policy gradient class of algorithms, it's been shown before. There's an Agarwal paper maybe I don't know now which one is the first paper, and we looked at log barrier approach, and this we showed for this log barrier approach. And for linear quadratic problems, it's also been shown. So like when people started to look at convergence of policy gradient in reinforcement learning, they looked at this problem, this gradient dominance property, and yeah. Good. Other questions? Okay, because this says that our gradient, I go back, gradient descent on this function, if you go to a stationary point, so theta k plus 1 is equal to theta k, and this gradient becomes 0, then you're approximately optimal. Yeah. Okay. Good. And so now we know that, okay, at least with gradient descent, if our log barrier gradient gets small, if we get to that point, we are approximately optimal. The next thing we have to take care is how do we estimate the gradients. So this is log this is j minus eta log of c of theta, so its gradient by just gradient of logarithm would look like this. And so we have to estimate this and the denominator, and the denominator is easy because you can, if you apply your policy n times to your system, you get n sample trajectories, and then you can do sample average to estimate c of theta. And then to estimate the gradients, we use the policy gradient theorem, which shows, just gives us a way to use trajectories to estimate the gradient of the cost function and the constraint. So, and just to formalize it, if this is our cost to go, so the cost from tau, not starting from 0, but for tau from equal to t minus 1, this is the cost to go. For a given state and input, expectation with respect to our stochasticity, transition kernel, and policy, then the policy gradient theorem says that the gradient of with respect to theta of j of theta would have this form. Okay, so here's our cost to go, here's gradient of with respect to theta of log of our policy, and here is the expectation, which means that, and this is sum over the time, which means that we can, if we can evaluate these for different trajectories, then we can also estimate this expectation with the trajectories, and that's what we do exactly. With the same trajectories that we queried our system, then we can basically replace all these terms with their sample, like replace that expectation with a sample average, and similarly do the estimation for c of theta. And then, so putting this together, we can estimate the log barrier gradient, and then we can also derive the number of samples we need such that with high probability, our estimator is close, sufficiently close to the true gradient. Okay. So just how many samples we need, so that by just directly using trajectories to estimate log barrier gradient, we have some confidence about our estimate. And we need to have some confidence because we want our gradients to be sufficiently accurate, so we converge to the right thing, and we also ensure safety. Okay, I think we're getting to the end. So the last thing we have to take care is how to choose this step size. And so this one has to be sufficiently large to make progress, sufficiently small to keep iterates safe. And usually if we knew this J tilde, we would use its smoothness constant to come up with some lower bound and upper bound on it, but we don't know it. But again, using sample averages we derive a quadratic upper bound at each point that we are querying our policy. With the sample averages, we derive a quadratic upper bound using the smoothness of the policy on the function, and that tells us how we can choose the step size. And because we know how accurate our gradient is, then we also have a high probability that this is a high probability upper bound. And so we can have high probability about staying safe when we take a step with this gamma k. And putting it all together, so we have that with suitable choices of this gamma k and eta, we have safety, so policies satisfy constraints with high probability, and we can, so for a given probability of alpha of satisfying these constraints, we can choose the samples large enough so that we satisfy all the queried policies are safe, and we also have convergence. Okay, so which means that theta of t with this many iterations we can bound its suboptimality, okay, with respect to j of pi star. And of course, this would depend on our epsilon bias, how rich our parameterization is, and other, and the accuracy of our method and number of samples. Okay, I think this is the last thing about this. So this was our latest result that build on a few years of work of first my student Ilnura Usmanova, and then Ting Ting. Ilnura looked at this problem in a constrained optimization setting, and she looked at if we have a black box constrained optimization, and we want to make sure we have a we want to make sure we have a feasible iterate method, but we don't know J and C. How do we do this? And that's so she initially proposed the idea of log barrier, but her work didn't extend to reinforcement learning. We applied it on RL, and it seemed to work fine. And then my student Ting Ting formalized all of that in the RL setting, and that required looking at this policy gradient dominance property and looking at how do we use policy gradient to estimate the gradients and so on. And the takeaway message from this, we can use policy gradient approach to solve safety constraint RL, and we can have provable safety, but with high probability and convergence, even in continuous state and action spaces, though here we have to rely on our policy parameterization properties being Fisher non-degenerate. But the sample complexity is also very high. So the number of it's worse than, so if we don't have these constraints, so here we need of the order of epsilon to the -6 to get some accuracy and safety. And it's not, generally these methods require a lot of samples. And when you have this safety and also feasibility, it even has more methods. And okay, like we are now currently trying to implement this and see how it would perform. Okay, so maybe just finalize my talk in the next couple of minutes. So in the beginning, I talked about the cost and constraints in RL are very important. And just the first takeaway message was if infinite horizon properties matter for our system, we shouldn't use a discounted or finite horizon RL cost. Maybe an average cost, or that requires maybe more work and study. Safety and reachability in finite horizon can be formulated through a constraint MDP over an extended state space. That's the second thing we showed. And then we can have this safe learning algorithm that ensures high probability safety during learning, and hopefully it increases trust in training on the real system. But I cannot for sure say that until we actually implement this on a real system. And so we are trying to bridge the theory and practice gap. It's difficult because I have some students who are very theoretical and some who are very practical. And it's, yeah, but I'm trying to, putting them together, see if we can just apply some of these theoretical methods to the applied problems. Yeah, so and to verify both on realistic simulators and hardware and improving sample efficiency of the algorithm. And we want to also, that's something I'm interested to look at, also generalization. How do we generalize to new environments? Yeah, and these are the references. And yeah, so this talk, again, as I said, mainly Ting Ting contributed to the parts I presented, Ilnura previously, and then with Yarden, who's a PhD of my colleague Andreas, who helped us with a lot of the simulations in the OpenAI and safety gym. And this is my group at EPFL, and yeah, so we're trying to work on these problems from theory and practice. So thank you. In the practical setting, I mean, in the practical setting, we usually know we don't want, for example, collision. So that's our safety. But because in RL setting, we don't know the dynamics, then we don't know functional form of those safe sets. Yeah. Yes, yes. Yeah. Yes, but a priori it doesn't know exactly where everything is. Yeah. It only interacts and gets some reward and penalty, and from that it tries to learn. Exactly. That's what yeah, exactly. Yeah. So you can evaluate your. Yes, maybe first I saw your hand. Yeah.
somehow I agree with the safety that need to be connected. But what if you have safety sets, sort of disjoint safety sets scattered in space? How do you make sure that not only one disjoint
okay, I think if it's disjoint, because all we can do is we can stay in the one we start with.
Yeah, so this is the assumption that the safety set is a connected set.
Yeah, because you cannot escape it. Exactly, you're right. That's a good point. Yeah. You cannot get out of it and get that. Yeah. 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 That's a good question. Yeah. No, no. So my student thinking, who is the theory person, thinks that they all have the same theoretical property if you use these other gradient estimators and so on. But I think in practice it could help improve the estimation. Yeah, I think it's a good suggestion. Yeah. Mm-hmm. 48. Okay. Where do you see? I don't. Where do you see slide numbers? Somehow I'm not in a full screen. Okay, maybe here. Mm. Here. I see what you mean. Oh, yeah, yeah, I see what you mean. For a given theta, you can evaluate it. Because you can, why? Because you get your trajectory and you can see if that one went to the goal set or not. Yeah, so for a given theta, you get a trajectory and then you know whether it reached the goal set or it didn't. Yeah. Yeah, because we formulated this property as one of QT being in the goal set. And that's as expectation of that. So this is like sample average estimate. Yeah. Yeah. Uh-huh. Yeah, but there's some probability you're not in the safe set. And on top of that, what we ensure is that, so if you write it, probability of, if this is our constraint, let's call it C, let's call it some, I don't know, F of theta, probability of F of theta being satisfied is greater than some other. So we have a double probability on top of that. Yeah, that's what the algorithm does at the end. Yeah. C is defined already based on our specification of reach, like basically this one. Our constraint now became, after we did this change, our constraint to reach this goal set and stay safe became an indicator function on this QT. Yeah. Yeah. What? Very infinite horizon. What did you say? Sorry, I didn't.
And then if I take trajectory randomly, the probability of hitting your calculation is by calculating how many trajectories are.
Yeah.
It might happen you very rarely hit them.
You what?
They only pick this small concept.
Yeah, I think in practice, yeah.
Then it requires
Yeah, maybe we can talk about that. I mean, yeah, this is the guarantee we have. Okay, with high probability, you would say you have an estimator and it has these properties, but yeah, I think in practice we would need many samples to have a good enough estimator. Yeah.
that's why.
Yeah, but this is also in a big O and it hides many things, and I really think in practice it would be very high. Yeah. Yeah.
What about the value function? I guess in this case, it's unaware of all the safety business.
Yeah, we didn't use a value function approach because I don't know how to do it with. So usually once we have a CMDP, people would, if you know the dynamics, you would formulate it as a linear program but using this occupancy measure, and you would solve it with that. If you don't know the dynamics, like the principle of optimality wouldn't hold once you have these constraints. And so we don't use value function, Q function. That's why directly you go to policy gradient, for example. To estimate the cost, similar to estimate the constraint. Yes. But I'm saying we don't use a method with like a Q-learning or a value iteration and so on. Yeah. Yes. Okay. Maybe like reinforce, but we did a fission on degeneracy to argue that we have gradient dominance. Yeah. Yes. But in natural policy, they use that as a preconditioner. Yeah, but we didn't use that, but we still needed to argue about this. Yeah, but I guess estimating it would be hard. Yeah. Okay. Yeah. Before? 4 parts. Okay.
So I'm asking that one. The reason I'm saying so because it's based on our perspective that we're assuming that
The safe set. We just don't exit the safe set. Yeah.
go outside the individual is the rate.
Yeah. Yes. Maybe we can discuss it later. Yeah, I think it's also a little bit confusing to think about it in the sense that actually this is our safe set, but once we formulate as an optimization problem, this C of theta, our safe set is about basically the set of policies that ensure this condition is met. Is not S, but it's the set of policies that ensure this condition is met. So now that I reflect, I think maybe my answer to your question about the disconnected was not quite accurate because we're considering the feasible set is the set of policies that satisfy these constraints. That's what we're looking at. And that we stay in that set. We start in that set and stay in that set. Does it make sense? You can talk offline. Okay. Okay. All right. Okay. Thank you for your attention. And yeah, I'll be here tomorrow. Yes. Thanks a lot.